Kingsley, what page? What page, King? Okay, guys, page 4, number 6 in the workbook. I assume you all have your workbook, right? So I need to borrow one somebody. Page 4, number 6. We've not covered that in class. You working ahead? No?
So I did a halo-hydrogen reaction, and I supplied it afterwards. I did a second reaction. I supplied
Which one? The first one or the?
Yeah, the first one. So yeah, I did a halo-hydrogen reaction. It shows iodine, and then I supplied with terpenolamine. But in your workbook, you use MCPDA, and then you supply with terpenolamine. I just don't see how the epoxide is going to. I don't see how you're gonna like lose the O, like, or open that ring after you.
That's what we're doing right now. We're going to the oxygen deleting group.
Would a halohydrogen and a terpenolamine still work?
Theoretically, but sorry. Thank you, Sadia. Theoretically, yeah, but what we're going to mention today is that oxides are great precursors for synthesis. And that's really what you want to see there is epoxide. Halohydrogen theoretically. But the more important thing is you were questioning how do you get the oxygen to leave?
Yeah.
That's more of a fundamental thing you need to make sure you. That's what we're doing right now. Okay, guys. We got a couple more minutes before we get started. Let's see what we got. We'll move on to alcohols today. We got a lavender. Then there was one I sent you by email. We got 2 alcohol handouts. Yeah. And then we have our epoxide handout that we're on. On this page. Where's this next one? Let's see where we're at. Didn't we end right here last time? What was the result of that reaction?
No reaction. No reaction.
Well, there's something going on, but there's no reaction with the epoxide, right? Why is there no reaction? What happens there? Formaldehyde is a strong base. You can't mix strong bases with strong acids, right? Game over. There's no incompatible. Let's see. I think we can get started. Yeah. Okay. Ready to go?
Yeah.
All right. Okay. Let's pick up right there. Kingsley, right here, the methanol attacked the carbon, the oxygen left, but it was protonated.
Yeah, I didn't see no protein in the reaction in the workbook. It's just in the epoxide.
Oh, by the way, the epoxide questions, list of questions are not in the workbook. It's actually in the handout packet, along with the answer key. Some of you noticed that. I just haven't got that added to the workbook. Okay, let's pick up right here. First off, let me make some comments about lab. We had first lab yesterday, another half of you have lab this afternoon. A few procedural things. TLC, first off, you got to review your techniques from Organic 1, right? Okay, we learned TLC, recrystallization, Organic 1. Many of you know there's a video on YouTube, my recrystallization video. Okay, I recommend reviewing that. TLC, you're just putting too much compound on your watch glass, not enough solvent. That's just wasteful. Also, your spouters are going to get clogged up because there's just too much compound, too concentrated. Some of you had cross-contamination. In fact, once Rachel, was that you? First TLC, it looked like it wasn't pure, but when you ran it again, it didn't look pure. Okay, I think it was cross-contamination. Lost and found box was, we added the number of items. So when you get through, you got to put your glassware away. So there was about 3 or 4 items that were left out. And also, guys, I mentioned yesterday about cell phones in lab. Okay? Please review the guidelines to lab. Okay, see you after you this afternoon. Let's pick up here with basic conditions. Under basic conditions. First off, I thought ethers were unreactive under basic conditions. Didn't we say that about like THF?
Yeah.
Diethyl ether? Okay. Well, that only applies to standard ethers. Epoxides, they are reactive under basic conditions. Like we said last time, ring strain. Okay? Because of the ring strain, they'll react, and we don't have to protonate them. We'll see examples of this. Instead of showing an example, let's get straight to some nucleophiles. What type of nucleophiles can we use that are strongly basic or strongly nucleophilic?
SP3, and anions.
Well, the first type we're going to see is acetylide anions. And this is largely reviewed from Organic 1. Remember we took an acetylide or an terminal alkyne. This H has some acidity because of the sp nature of the carbon. Okay, we can deprotonate it. Remember we used like these 2 bases in Organic 1. Sodium amide. Basically this is your it's an H2 minus, right? Because sodium is plus. We get rid of the spectator ions. These electrons take the H. These electrons stay behind. What do you get? Lone pair of carbon. What do we make? Ammonia. We can also do this with n-butyl lithium. Of course, n-butyl lithium is just butane with an anion. Lithium there. These electrons take the H. Electrons stay behind. Same thing. What do we make? We make butane there. Okay. Question?
You said that epoxides, they're reactive with bases because of the fact that they have ring strain, but what if you had a 5 or 6 member ring? Would that also be reactive under basic conditions, or would that?
Well, if you go back and look at THF, where's THF at? Oh, that was on the ether handout, the previous handout. THF, 5-member ring, we said it was not reactive. Okay, 3-member ring is reactive, but not the 5 or 6. So in Organic 1, we pretty much just made these. We didn't use them. We just illustrated the acid-base chemistry of Organic 1, right? We may have used them for like an SN2 or something, but not often. But now we had to do epoxide chemistry. Strong nucleophile. It's a carbanion. Okay? So in our epoxide, this oxygen will leave one of these carbons because of the ring strength. We do not have to protonate in epoxide. That's the major thing right here. Yeah? Okay, which carbon are we going to attack, left or right? Either, symmetrical. Okay? This is actually the most simple epoxide you can have, just a 2-carbon epoxide. It's called ethylene oxide. It used to be used to, it's a gas, it used to be used to sterilize instruments because it would react with all the microbes and kill them. I don't think it's used much anymore. These electrons will do what? Which carbon do you want to attack, Rosmika? That one. Either one. Electrons up, right? Electrons away from carbon, what does that give? Well, we got, boom. This carbon is now bonded to what? That carbon. So we'll call it that. What else is there? We have that carbon. What's on this carbon?
O minus.
The O. And what's the charge? Negative, because 2 lone pairs there. What does this arrow mean? Bonding pair moving on to oxygen. That's third lone pair. Third lone pair, it's a minus charge. So this is what do we call this in terms of our terminology? Strong nucleophile adding to an epoxide, opening it up. This is our outcome. Importantly, is there any proton we can put on here in the reaction? There's no proton. By the way, what I drew there is what I got here, right? No proton. The proton, to go neutral, has to come from a separate step. You have to add in a proton source. Your favorite H plus source. What's your favorite H plus source?
NaH or
No, NaH is, that's an H minus source, right?
so HX.
HF?
HX.
HX.
Yeah.
Okay. Like HCl. Yes, you can throw in some HCl. Now supply proton. You can also throw in water, because this is pretty basic. Water is acidic enough to supply proton. These electrons attack H. These electrons move here. What do we get? We get that plus what? Hydroxide, if we use water. That's an equilibrium, but that's all you really need. You extract this or something. So we do need a workup step. In most of my examples that I give you, example reactions, I'll call this workup or appropriate workup. You got to be careful. A lot of times people just assume that you're doing this, and they won't even give a proton source. They'll just expect you to supply the proton. There's no proton in the mix. We'll say this, let's look at the product. Which bond did we make here? Did we make that bond right there? sp carbon to sp3? We'll say this a number of times moving forward. What type of product do you get when you add a nucleophile to an epoxide? Yes, alcohol. What was this portion called back over here? General name. Nucleophile. Right? Everybody agree that was a nucleophile? Here's what epoxides give. Nucleophile, carbon, carbon, OH. Nucleophile, carbon, carbon, OH. Because you get nucleophile bonded here, that's one carbon, then there's another carbon, and then the OH is going to be on this carbon. After it leaves, it becomes OH. So acetylide anions is one type of strong nucleophile. Let's look at another type.
And there's always going to be 2 carbons between the nucleophile and the oxygen, or the OH.
Well, the short answer is yes. But why? I mean, the epoxide is 2 carbons. And when the nucleophile ends up bonded here, and this leaves, eventually becomes that, what do you have? Nucleophile, carbon, carbon, OH. Okay, the next type of strong nucleophile is actually quite famous, and it's got a name called like Grignard Reagent. We also have alkyl lithiums. Okay, we get acetylide in here, SP, like an alkyne anion, called acetylide anion. What about just a regular alkyl anion? For example, this. And we've seen this before. This is N-butyl lithium. Could this be a nucleophile for an epoxide reaction?
Yeah.
Yes. Sure, it could. How do you make these? You might say, hey, let's take butane. What do you want to do with butane to make this? Remove an H. You want butane to act as an acid. How acidic is butane? It's like, yeah, greater than 40. It's the least acidic compound around. Taking an H from just an R group, alkyl with a base to make the anion is very difficult unless the R is sp, like we did above, sp. This is very difficult, usually not done. Instead of doing an acid-base reaction, we do more of a tricky reaction that is more of a redox. What we do instead is we have an R group with a halide on it. Okay? Put a halide. Now, if you want to maintain four carbons, we've got to draw an extra bond and maybe do something like this. So this is this. Halide can be anything, usually not fluorine. It can be really any hybridization. sp2, sp3 is fine. We react these with a metal. The metal will insert. I pretty much summarized it here, so let me kind of show up here. So take this, react it with a metal. Actually, I think I spell it out on the next page. Yeah, I do. I'm not going to redraw it for you. We'll just discuss it sort of here. We'll sort of go back and forth. This is the chemistry. The summary is on the previous page. Let's look right here. I just got 3 carbons. You take like an alkyl halide reacted with magnesium, which is the most common. That's magnesium metal, right? Oxidation of 0. These are just solvents. The metal will insert between the carbon and the halogen. That's what I showed here. Now, how does it do that? It's most likely redox. Okay? And very typically, when we do redox, it's hard to show mechanism. It's probably a radical mechanism. And we're not going to show mechanism. It's just inserts. We got here. Now, one thing we can say is, well, let's first show the structure. The structure, well, magnesium tends to be ionic or covalent? It tends to be ionic. And if you show this ionic, what would the charge of magnesium be? 2 plus, as usual. Somewhere up there. What's the charge of the Br? Typically minus. The other part, which is your propyl, what's its charge thus going to be if we balance this out? Minus. How do you make it minus? Well, it's going to have a long pair. It's going to be minus. The chemistry that takes place, the insertion, essentially leads to this. It's usually showed sort of just together, like it almost looks covalent. It's somewhere in between ionic and covalent. But it's essentially, this is essentially what? Essentially what I showed there. We get what we want here, and it will react as a carbanion. And we do this, instead of removing an H, you could say we remove a halogen, but it's an insertion. Why is it redox? The oxidation state of the magnesium is what here? 0. What is it now? 2 plus. So the magnesium has been oxidized. What's been reduced? It depends on how you do redox, how you do oxidation state of this, which is a little bit cumbersome. But something's been reduced. Typically, when you add electrons to something, you consider that reduction. We kind of say this has been reduced. Okay, it's a redox reaction. When you do it with magnesium, this thing here, or shown like this. Whenever you see this, how do you think of this? R minus. It's that portion minus. These are called Grignard reagents with the magnesium. Because Victor Grignard, back in like 1899 or so, was first one to say, hey, what if I add magnesium to 1-bromobutane? He added it in, maybe with some ether, heated it up, it became exothermic, and then it took on new properties as if it was sort of reacting like this. He won Nobel Prize in like 1905 or so. Huge reaction, really changed the course of organic chemistry in the first half of the 20th century. Because then chemists started doing so much with these nucleophiles, building molecules. You can also do this with lithium. Lithium's a little bit different because lithium is group 1, right? Okay? Lithium, you have 2 equivalents. You get this plus lithium bromide. And of course, if you look at this, what do you see?
Lithium plus.
You should see that and lithium plus. So there you go. That, this, they both give these nucleophiles.
Okay, I mean, is the reason why you need 2 equivalents because the bromine wants to be with the lithium in a solid?
Right. If you only use one equivalent, what would be the fate of your BR?
Okay.
If you just think about it, it's see with the Grignard, you sort of have equivalent amount of charges there, or everything can just exist as one species here. You got to have 2 up there. Now we've used like n-butyl lithium before as bases. They can be used as bases. Okay. Now probably on the previous page is just kind of summarizing that stuff. There's an important point over there. Very important point. Right here. By the way, terminology. If it's got a magnesium, we call it a Grignard reagent. What do you want to call this? Very good, Michael. Tell us again.
An alkyl lithium?
Alkyl lithium. These are typically referred to as alkyl lithiums. A broader term is organometallic. What does that term mean to you? Organo? Organic. What does metallic mean to you?
Lithium.
All right, it's lithium. It's called an organometallic reagent. Sort of makes sense, right?
Yes.
Okay, so we're dealing with organometallics. These organometallics, none of them can exist in the presence of an acidic proton. If you try to use ethanol, maybe a solvent, that's a poor choice of solvent. Because this is a very strong base, it'll just take that proton and you'll protonate your nucleophile and game over. It's no longer a nucleophile. Okay? Choice of solvent's very important. What's a good solvent for these strongly basic reactions? DHF. Who said that? Varsha. Must have been the win. Varsha? No. THF or diethyl ether, which we said were good solvents for strongly basic reactions, right? Yeah. All right, let's see if we can use these reagents. All right, here we go. We got this. What would lithium do to this? By the way, there was one other piece of terminology, I don't think I used. When the metal adds, the metal gets oxidized, right? Yes. These reactions are also very generally called oxidative additions. We say the magnesium does an oxidative addition to the alkyl halide. What's the first step here? Lithium does what? Oxidative addition to the alkyl bromide, and that's going to give, let's go this way. What does 1 give? It gives that, right? 3 carbons. Plus what if we want to show everything? Yeah, but this is what we make with step 1. Step 2, we throw in an epoxide. Will a strong nucleophile, what is this? This is essentially this, right? Okay? You got to be careful. You can find book chapters about the structure of these. They're complex. They're known to exist as trimers. This is sufficient for us to understand the reactivity. Will that react with an epoxide?
Yeah.
Sure. Epoxide is very electrophilic. Which carbon are we going to attack? Left or right? Why right? Why sp2? I mean, why SN2? Did you read the bold heading at the beginning? Okay. Whenever you react epoxides under basic conditions, strongly nucleophilic, the mechanism is always what? SN2. Okay? With acidic conditions, you have choice. Basic conditions, always SN2. Yes, it was written in bold at the beginning of. Okay, since it's SN2, which carbon are we attacking? Attack the right. Electrons, oxygen leaves. What does that give? I'll go this way. Let's see. There's the epoxide 2 carbons. Here's what we attack. What does it have bonded here?
Which way are you going? Are you going to the nucleophile or to the oxygen?
This is the 2 carbons of the epoxide. And this is one we attacked. So what bonded here? A propyl, right? There's that bond. Propyl was a nucleophile, okay? What is on this carbon? Oxygen, which was the leaving group. Right? What did it leave? It left that carbon here when the nucleophile came in. What else is on this carbon? Methyl. Is it bold or dashed? Sure, it's bolded. Why is it still bolded?
We didn't do any chemistry there.
We didn't do any chemistry over here. There's your product. Should we have an H here yet?
No.
No, there's nowhere for it to come from. It's not going to come from a CH. What's appropriate workup mean?
Provide a proton.
Add acid.
This is what we said. It adds water or add your favorite acid. And so I'll do this out this time. H2O workup or acid workup, etc. Basically, you get the same product. Except now it's the alcohol, right? It's protonated. Which bond did we make? Right there. Anytime you react epoxide with a nucleophile, what type of product do you get in terms of nucleophile? Nucleophile, carbon, carbon, OH. Now there may be other stuff on your carbon, carbon, but you'll also always have nucleophile, carbon, carbon, OH. How about the next one? Why don't you take 2 seconds to do the next one? And then we'll look ahead to amines. What's going to happen with magnesium and iodobenzene? Oxidative addition. Okay? Right? Magnesium iodide. But what is this essentially? It says anion, right? That anion, I minus and magnesium 2 plus. Isn't that an amazing reaction right there? Yes. I haven't seen it yet. All right, we put an epoxide in here, what can happen? Epoxides are very electrophilic, ring strain. Standard chemistry, nucleophiles adding SN2, right? Strong nucleophile. Which carbon we're going to attack? Attack the left. Take the oxygen off. We have stereochemistry at this carbon we're attacking. I'm just going to call the ring phenyl. I'm going to draw my product like this. Here's the 2 carbons of the epoxide. That's what we attack, but let's move over here first. This oxygen's in the plane here, okay? It just opens up, but it's still in the plane. So I'm going to just draw it straight up. The ethyl is still back, and the methyl is still forward. The nucleophile is here. Everybody agree? We added it there, we bonded it there. How do we want to draw that nucleophile, the benzene ring? Shelby?
Or in the dash one.
You want to draw the phenyl with a dash? Forward? Why forward? Attacking here. I'm going to draw the benzene ring, which I'm going to note as phenyl, straight down, right? Why straight down? How's the leaving group on that carbon? Is the leaving group forward, back, or straight up? Warren? The oxygen is straight up. If the leaving group is straight up, right? How's the nucleophile going to come in? Straight down, right? It's not going to come in from the front. That's not backside. What's backside to straight up? Right here. Yeah. How are we going to draw the methyl? We're going to draw it bolded. And there's our product. Now I'm not going to redraw this because we want to save 10 seconds. But with appropriate workup, what happens here? This becomes right. Okay? There's your product.
Why isn't there an inversion from the phenyl chlorine?
There was an inversion. We did inversion.
Oh.
No. We did inversion.
Like, why is it a bold dash?
Why is this not dashed?
Yeah.
Okay. We might need a model, but sometimes it's good to just use your hands here. Let me, okay, here's a fancy model. The leaving group is straight up. This methyl over here is forward, correct? So this is the methyl forward. All right, I need a participant. Okay. How does a nucleophile come in? Okay. Now I want to stay like this because that's the way it's on the board. You can be over there. Methyl forward.
It's right here.
Okay, when it comes in, what does it do? It kicks this off.
Right.
Now it's down. But what happens to these two groups? They just go up. That's your inversion. So now the methyl, instead of but it's still forward, right? It's just sort of up now. All right. Let's do it another way. Yes. Let's do it like this. Let's do the same chemistry, except let's say the methyl is forward. Now, you've got to come in here. Same thing. The methyl moves this way, but now it's what? Now it's back. But it's the same thing. It's just forward and back is... It's like now we move forward and back this way. If you want to do R and S, what is this? RS. 1 carbon oxygen 2, carbon methyl 3. What's that? R? What is this? And see, we really don't need to be doing this because this could not turn out right. Carbon oxygen is 1. Phenol's 2, I'm sure that's 3. H is in the back. What is this? R. Yeah. See that we shouldn't have done that. Trust me, we did inversion. If you understand what inversion is, the only difference is we're coming in straight down, things just move straight up. If you have questions, ask. Okay? And this is the case, Jordan, I think, where the priority switched, and that's why it's still R. Remember the question last time?
So is this just like always the case for epoxides?
Is what the case?
Like basically we're like, what the inversion just teaches it like changing. Like the RS doesn't change.
No, that was just
Coincidence?
coincidence. And I hope I get R and R correct. Did the thing make sense? I mean, leaving group expelled, nucleophile comes in opposite the leaving group. What happens when you do that? These move up, right? The only difference is I'm going straight up. If I was like this, my elbow would be back, and when I did this, it would be forward. But that's not how it's drawn. Instead, it's drawn like this, and okay? It's still inverted. All right, let's look at a different nucleophile. So there's plenty there. Like I said, the practice problems are not in the workbook for epoxides, but they're in the handout. And the answer key is in the very back. Amines. We learned in Organic 1 that amines are they're good nucleophiles in the neutral state, right? So ammonia is a good nucleophile. Tends to be basic, so we're doing what mechanism? SN2. So these electrons attack here. Kick these off. What are we going to get? This is up. Leaving group got kicked off. But it's still forward. I mean, it just gets kicked off with that carbon, but it's still forward. Nitrogen not bonding here. How do we want to draw the nitrogen? Yeah, see, this is easier. More conventional. But if you really understand inversion, see here the leaving group is forward, and so the nucleophile is going to come in back, kick it off. So this is going to be dashed. What's on the nitrogen? 3 H's. We don't just magically lose the H's. Who? What? They're going to go where? You have a built-in acid-base reaction. Do we need to supply proton to get the H here, or is there a proton sort of supplied in-house? This looks like an acid. That looks like a base. You're going to get a... now, I call it H plus transfer. You could call it an internal acid-base reaction. I'm not going to do mechanism. Does that look right? Yeah. And when the proton gets transferred, we end up with this neutral product. Here you got a proton that's available for transfer. Everything goes neutral. Joseph, right? Yeah? You're shaking your head, right? Sounds good? What was this in the original generic name? Nucleophile, carbon-carbon OH, right? Two steps. Show the product of this here. And then we can also be looking at that one. What we're going to do with epoxides is we're going to move into multi-step synthesis. And epoxides are very versatile for doing synthesis. Very commonly used. So this is just a two-step synthesis. What does MCPPA do to this molecule? The epoxide. Yes, that's Carl, but is it going to be R, S, or what? I thought that was going to be easy. Racemic, right?
Yeah.
I mean, that's not optically active, so this can't be optically active. Here we go. We now throw in amine, epoxide. What does this look like? Amines are good nucleophiles. Epoxides are known to do what? Have nucleophiles attack them. These electrons, everybody say it with me. These electrons do what? Attack right. Why are we attacking here? Least sterically hindered. SN2 is governed by sterics. Kick that off. What do we get? Go ahead and show the product while I'm erasing here. Dave?
Is it, so you just did the chapter automatically, you want us to do that one?
Well, I didn't do mechanism. Ultimately, that is a part of the mechanism, and we get a neutral product, right? Yeah. And there you go. There's your, in terms of predicted product, okay? Isn't that the final product? What bond did we make? Right here? Nucleophile, carbon-carbon OH. Nucleophile attacked the carbon, kicked the oxygen off. The oxygen became protonated and proton transfer. That's a two-step synthesis. Variety of other strong nucleophiles. I can't cover them all. You should be able to recognize a typical nucleophile. How about right here? Can you show this product? What's the nucleophile here? Osmat?
Methyl oxide, MEO.
MEO what?
Negative.
Yeah. K plus, right? That's what this is. I mean, methanol is also a nucleophile. Which is stronger, anion or neutral? Anion. It's there. Use the strongest nucleophile available. Okay, this nucleophile, these electrons, we're going to attack left or right? Take that off. So show product. Ah, okay, we're back to some stereochemistry that we need to be able to work with. Good question. Before we work it up, it was originally this, right? first off, before we move on to the proton, is this right in terms of product?
Yes.
Very similar to that one we did before when we were doing this. Leaving group is straight up, so nucleophile is straight down. When the nucleophile comes in, the methyl just moved up. Where can this proton come from? There's somewhere it can come from. Come from the methanol. Okay, I'm not going to redraw the structure. Some of these reactions, you might have a solvent that can supply the proton. Okay? Nucleophile, carbon-carbon OH. We'll finish up on the other side for... I've been looking at the epoxide puzzle. I mean, we have an epoxide here reacting it with dimethylamine. Can you already envision the mechanism for that? What's going on? Basically, there's lots of practice there. Most of those problems include stereochemistry. Some of you have already figured out the answer to the puzzle. Let's see. Okay, let's go back to synthesis. All right, we alluded to it. Let's allude to it again. And eventually we'll sort of cover it. That's not it. Use of epoxides in multi-step synthesis. Epoxides are a great source of 2 carbons and an OH. Thus you can get out of this, I don't know if we've said this, but you can get nucleophile, carbon, carbon OH. Okay? You can repeat that tonight before you go to bed. Now, if we look at a product, we're back to where you Kingsley asked this question earlier about that. I think that was it, yeah? What did terbutaline? Terbutaline is used to control premature labor. Anybody familiar with terbutaline? Nursing or anything? Yeah, Larry?
My wife was on it for a little while.
How could we, now we're going to focus in on epoxide reactions. How could we make this through an epoxide reaction? Let me ask you, do you see nucleophile carbon-carbon OH in this molecule?
Yes.
So Ronnie, what do you see?
With the amine there and then carbon-carbon.
Amine, carbon-carbon OH? So maybe we could have that be nucleophile, and these 2 carbons were originally what? Part of the... Maybe these 2 were part of the epoxide, maybe? Now this over here is just going to be decoration. These are, y'all heard of catecholamines in like biology classes?
Yes.
Yeah. With the 2 OHs being meta, it's a catecholamine, right? What would we need to react this with to get this molecule? The nucleophile. What is a nucleophile? That. Now you could use minus, but with amines you don't typically need to use minus. It can be just neutral. And if it's neutral, it can just be NH2, right? And of course, I'd probably draw this, just something like that. I just do the bond down. Now we can say, hey, this is how I'm going to synthesize this using an epoxide. These electrons attack where? Left or right?
Right.
Here, kick that off. What does that give? It gives a structure that you have to do proton transfer, and after you do proton transfer, what do you get? You're going to get that. Okay? Of course, I can't draw it out every time. You need to go home, go back through it, do the steps, see the proton transfer. The bigger thing is nucleophile, and we can see this in the molecule, and we can say, hey, I know how to synthesize that. All right?
You create the epoxide reacted
Okay.
with NTP.
She's basically asking, how do you make the epoxide? Well, right now we just did kind of one step. Maybe we can look as we finish up some problems ahead. Let's skip ahead here. Next page. Actually, instead of doing the polymerization, let's skip to this, because we're ready to talk about it with this question, etc. What do you have to begin with? In multi-step synthesis in organic, sophomore organic classes, typically you're asked to begin with a certain starting material and then get to where you're being asked to go. And it's not always just 1 or 2 steps. By the end of this semester, we'll be doing 6, 8, 10 steps. But that's just like learning to read. We're going to learn to read, then we're going to read a novel. I mean, once you learn to read, you can do as many as you want. Now, we're not MacGyver. We don't have to start with carbon and like paper clips, all right? And you know, of course, most of you don't even know who MacGyver was. Unless it's on like, what is it called?
Netflix.
What's TV Land? Let's do this one down here real quick. Synthesize this compound starting with styrene. Now when you do synthesis, you do not actually start with styrene. That's not the way to think about it. We want to start here and go backwards. It's called retrosynthesis. What's the main functional group here? An ether. The first thing we want to do is, how would you make this ether? Eventually we got to get 2 carbons added to this, because here we've got 2 extra carbons. But let's not worry about that yet. How do you make ethers? Williamson ether synthesis. Back this up to a Williamson ether synthesis. This is a retrosynthetic arrow. I would say, I can make that compound this is what I'm proposing. We're going backwards. I'm going to propose we say this. If I had this, or if you had this, could you then make that?
Yeah.
Coming forward, what would you do?
Sodium, methyl iodide.
Sodium, good.
Methyl iodide.
Not ethyl. We don't need an ethyl.
So methyl iodide.
We need a methyl, like methyl iodide. That's a standard Williamson ether synthesis. Basically, when you synthesize something, you build a larger molecule. So if we go backwards, we want to go to smaller molecule. This is smaller than that. Now the chore becomes, don't make this. Now we just need to make this.
Okay.
And let's finish up in the next 1 or 2 minutes. Now we come back to, an alcohol. I don't know if we said this, but oxides are good reactions. They ultimately give alcohols when you react. Not only do they give alcohols, they give nucleophile carbon-carbon OH. Could you back this up to an epoxide reaction?
Yes.
Am I missing a carbon?
Yes.
1, 2, 3, 4. Yeah, I thought so. Okay. Nucleophile carbon-carbon OH, Could that portion be nucleophile carbon-carbon OH? I'm going to back this up to this epoxide, which only has 2 carbons. What nucleophile do I need to react this with to get that? An ethyl anion, which comes from what? Like an alkyl lithium, or I'll abbreviate it, maybe ethyl magnesium bromide. Okay? But if you had these 2 and reacted them, would it give this? You got to work it up to put the proton on it. We're asked to start with this. Can we back this up to this?
Yes.
Or come forward. If you come forward, What would you do to this to get to that? MCPBA. There's your synthesis. Take styrene, MCPBA, make epoxide, react it with the appropriate nucleophile to give this alcohol, then finish it up with the Williamson ether synthesis. There's others on here to work. Some of them include chemistry we haven't covered yet, which we'll be doing on Monday, which is the oxidation of alcohols and alkenes. I'm also going to send out a answer key to the NMR warm-up page. Have a good weekend, guys. See some of you this afternoon.